All right, I just wanted to go over some of the details about like what I built and how it works and where it's going and how it's going to get there and stuff. All right. Um, so first of all, I made a lot of changes to emulator.js. And rewrote all of the netcode in there and added some settings functions in there. And that's a big part of all of this, is rewriting it so that it calls to a different type of NetPlay service, and heavily rewriting it was necessary to get this all to happen. What else I did was I built an SFU selective forwarding unit based on MediaSoup. MediaSoup are these libraries that provide ways to handle video and audio and data streams and stuff like that. And so, but I had to build the actual server, air quotes, part, which is a Node.js script here. Although MediaSoup is compatible with C++ projects for native code as well, but this is, that's not what we're building. So we've got the SFU server here, and initially I managed to get the emulator to talk back and forth with the SFU after enough time, and I got it to talk back and forth with another emulator. But then it needed to talk. Well, I can't slide the screen around easy, huh? There. So then it needed to talk to something else to get more functionality. It couldn't just, it needed to do a little more, and I had other ideas for what to do with it, so we need to connect it to Redis. And we want to communicate with Redis because it can store expiring data about rooms so that it doesn't require cleanup scripts. The SFU, it handles sessions and rooms and cleans up after itself, and we'll go there after. Actually, we can discuss some of that now. So we'll go over here. This is our SFU server, and basically it'll host a router, and it can host many routers, and a router basically represents a room. And from a router, we've got a video, and we got an audio, and we've got data, and a room can support an arbitrary number of or a router can support an arbitrary number of these going in any which way that we want to send them. And it also packages this kind of stuff into a worker. And so there might be another router on that worker. And a client PC will connect to the router and say that I want to produce data. I want to produce video, and I want to consume data so that it sends video and it consumes data. So it sends video and audio and it consumes data, and another PC connects, and just based on the way we've got things set up right now, this is how it goes. Video and audio, and it sends, it consumes video and audio, and it produces data. So these are terms because this is what the software uses for terms as well. As a producer is producing. It is a term for the host produced video feed, or the host produced audio feed, or the host produced data feed. And the SFU acts as a central point for all these guys to send data back and forth. And the way we wrote emulator.js is it doesn't actually just exclusively have to use this. We can say we don't want to send our data over this. We can send our data directly with P2P if it's negotiated. So we can use the SFU for the video, and we can bypass it for data inputs. So that data inputs are faster, lower latency for data inputs. But the SFU router, it handles video just a lot better. Like even in a one-to-one situation, it's handling video a lot better than P2P can. It's just got intelligent features for managing. It's got support to build intelligent features, I should say, for managing bit rates and bandwidth, and it's also capable of, so these workers, you can have more of them, and each worker represents a CPU core on the host machine. And so you can support a lot more clients and a lot more sessions on your SFU if you multi-thread and set up multi-threading. This framework, it lets us, we can do all kinds of things, like we can use the use it as a data relay to synchronize data back and forth. Like by that I mean like time synchronize it. It can be taught to, the SFU server can be taught to predict the latency of a person farther away compared to the person closer, and we can have all inputs come into this, and it'll send them back out with little predicted gaps in the stream, or in the timings of the data packets that it sends. Predicted delays in order to try to match up the times that each client receives the data. so that they would all be receiving data at the lowest common denominator for latency, but they would be receiving it in sync at least, and that's a kind of a feature that we could use in a implementation for rollback netcode, which can still rely on P2P, but in the event that P2P can't be used, or in the event that we want to have rollback code implemented in a 4-player lobby, we can use the relay for that to sync up. Because when you have four PCs and they're all sending inputs back and forth to each other, all at the same time, that gets heavy, and it causes a lot of problems for rollback and sync net play. You can scratch all that and you can have just one-way data streams back and forth. Each client only sends one data channel and only receives one data channel, instead of this big mess with 3 or 4 different connections going every which way. So it is more optimal over here than over here in pretty much all cases. Now, so we built this SFU and it communicates with emulator.js. And we also like to use the Redis server because we don't, I implemented it once in the testing environment, but I don't actually like it. What we're doing is we're using an API from the website. This is our website, and it has an API endpoint, and the SFU communicates with the API, and the API and the website itself talks with the Redis server. So the Redis server stays on the same container as Romm-M, and it stays locked down in protected mode, the way it is right now, so that the only thing that can communicate with it is the local SFU, or so the local Romm-M instance, and anything running directly within the container for Romm-M are the only things that can communicate with the Redis. And they also need to know the secret key. There's a secret key that only Romm-M has, and it's used for the Redis access. It's also used now for minting tokens. It mints these tokens, and they have an expiry. They are timed, and they get requested through the API by the SFU. And the SFU has its own secret. And the SFU verifies back through the API, and it uses its secret in order to communicate with, to authenticate its communications with the API. And so it almost seems pointless here, but what this is doing is It's securing access to the SFU. It's protecting it from random shady people on the internet. They can't get in anymore because what we're doing is we're storing the token in a table on the Redis database that's in a dictionary on the Redis server that is associated with metadata it can be associated with metadata about the user, and we can create persistent netplay IDs based on this. So it currently has a rudimentary implementation. So when SFU allows a client to connect to a room, they create a user ID, which is a random identification number that is used to for the rest of that session, and it identifies who that user is on the server, basically. And so it like sort of vaguely, right? It's very it basically associates it with their data streams, and so at a basic level, the user ID can be spoofed, and you can hijack data streams and video and audio streams and stuff like that. And you can spoof, like, you can spoof and get access to things with that. It's not good. So we have security measures against that to prevent hijacking streams in general, and we have enforcement in place, and we have a preference to cross-check stuff like the user ID with the token authorization, and we have steps in place to prevent duplicate IDs being used and stuff like that. And so there is because of that, only with all of this, there's only authenticated users of the Romm website allowed to access the SFU. And if you try to join a router or a room where you are logged in on another computer or another browser with the same account from Romm, normally it would assign you a generic random user ID from here, but I've implemented it so that you need a genuine ID from here, so you will not be allowed to join the room if you are logged in on the same account. It's just part of the beginning of the framework for persistent netplay IDs. Basically, it's one session per user, and if you want to netplay on multiple sessions, you need another user, and you need to be a user to connect to the SFU. It's not going to tell you anything about what rooms are open, because there's a call that they put out to ask what kind of rooms are open and what kind of streams are in that room and how many people are allowed in that room. that kind of data gets stored here, but it can't store, SFU can't store stuff like what emulator is running or what ROM is running. And so that's also why we need this channel here, so that later we can introduce more metadata about the rooms, like what emulator is running, what ROM is being played, and we can say, and we can even say, we can show that on the screen, and the API can feed that metadata to the to the client or the SFU, and they can use that in their lobby to provide a more rich experience in the NetPlay lobby, where they can see more stuff like cool pictures about the game that's being played, like cover art, or we can enforce. So currently it's a live stream session type, but we'll get to netcode, rollback netcode, and sync netcode, and we'll need to enforce matching emulators and ROMs at that point, because people will be running their own local instances of the emulators rather than sending video streams back and forth. And so there's more to this, because we can get more SFUs and we can create tunnels. There's a tunneling protocol we can use that connects the SFUs, where they symbiotically share information about their rooms. And they can maybe share a little bit of basic information about where they come from and what network they belong to. And so this guy can communicate to this guy and tell him, I've got these router IDs and these user IDs, or such, and you can give a limited amount of information too, right? So like, we can have this guy, if he wants to create this data channel, we can have the SFU say, nope, you have to get a token, and then I'll open up a tunnel for you. And then he opens up a tunnel, and then he shows all this information about the session, and then this guy says again, hey, I've got this information about the session, can I get a little more information? And this guy goes back to the Redis and sends it out the API endpoint to this guy, and then he knows a little more information about it, or he sends it to the clients directly, because this guy will have his own clients connected here. And so this SFU can be, these SFUs can be both owned by us, and we can manage and administer them all on our own completely. They'll be part of our own mesh network, and there will be load balancing. If this CPU gets too tired, we'll draw a little sweat. He's too tired. He's got too many computers going here, or maybe this guy is just too far away from this guy, so he'll connect to this SFU instead, because this guy, he'll try to connect to this guy, and he'll be like, yeah, well, you're authenticated, but I'm pretty tired, so I'm going to send you over to this guy, and so that'll get managed that way. And But we don't have to own this. We can create something bigger. We can create a federated authentication network with another ROM-M site over here, and it has its own tokens with blackjack and its own API. And its own Redis server. And we can use a public-private key exchange between the two. And we can save it in a file named after the website. We'll save their public key in a file named after their domain name, their FQDN. And when they try to communicate from their API to our API for authentication or metadata to our SFU, authentication to our SFUs, or metadata about the rooms that are running on our SFUs, we go through the API and we check our public-private key matches with, is valid, and we also check that the traffic coming from them is coming from their fully qualified domain name over SSL, so that this guy is our friend, but we make sure that we're communicating with our friend and not this guy with the sad glasses, because we have a thick layer of security here, because there's the public-private key, but there's also certificate authority authenticating their SSL traffic over HTTPS. And so they authenticate their own SFU. They get authentication through this method so that their SFU can create a tunnel with our SFU in order to share room data, right? So now we have all of this information being shared with our friend's SFU. And if he needs more data about the rooms, he has access to the ID numbers for the rooms, and he can ask for them through the API and then give them to his client, so that this way his client can securely authenticate. He can authenticate to his own SFU, and his SFU will open up access to all of this stuff, and his SFU acts as a gateway to our network, and we can maintain control of our own limitations on the SFU servers. And he maintains control over the limitations and logic of his own SFU server. And they could set up custom limitations for federated friends like us and vice versa. And even if this guy decides he's going to travel, he's got his phone with him, and he's traveling now. He will maybe be closer to this SFU, but he'll connect to his and his home server for authentication to talk to his SFU. His SFU will say, this guy's a lot closer. His SFU, who's been authenticated with our SFU and established a tunnel already, will say, hey, these rooms are open and this guy over here is hosting. You can go play with him. But also, if you're gonna, this guy's closer to you than you are to me, so why don't you just connect directly to him? And that won't be a problem because we've already implied trust and authentication through him verifying on his own SFU and his SFU verifying with us. Or his API verifying with our API, and so on. And we can safely assume that they aren't messing with things because they've got valid token checking in place with our own service here. But this is potentially, now that I'm thinking about it, maybe this guy wants to take out the code where he authenticates the users on his own service for some reason, and just let anybody connect, which would open up. We can take a look at that further, though, if that's a serious concern. And there's probably a way we can enforce deeper authentication of individual users from federated sites. But we'll also have identification, because we have persistent identification, because sessions are no longer just about the user ID that gets generated per session. They're now about a persistent identity from the Romm-M server. We can also tie that in with the federated network, so we can identify not just that this is ID unique person 1234, it's unique person 1234 from site B, and we'll know that, and we can show that in NetPlay. And because we have persistent identification for players based on what server they're from and what their unique ID is, that is something immutable about them, about their account, then we can enforce more social features. We have a way to tie your gameplay in NetPlay back to your account. At a very minimum, it's going to be very easy to link your profile in NetPlay to your profile on Romm-M and present stuff like RetroArch achievements that way in maybe like a pop-up window when you click on a user in a NetPlay lobby. Or we can enforce ban lists that have persistent ban on a user until they go and make a new account. on their server. But that's the possibilities here. And so some of the other things we'll be able to do, like I mentioned, is we'll have rollback netcode where we only send data back and forth, and the two servers, the two clients try to try to keep in sync by save stating every frame and rewind or reload back to a frame or two if the inputs get out of sync, and they will then kind of fast forward through the frames in order to catch up, and it makes some things look a little move faster, but it does like cover up lag issues, and it's kind of the preferred way of running like more professional competitive 1v1 fighting. And it's going to so we'll do that by P2P mostly, is going to be the preference for 1v1. And when there's 4 players that want to play Mario Party, which can be a pretty high-paced game, it's going to be sensitive to inputs and timings. Then we have the option of the server. And Mario Kart too, where you're racing, right? Then we can use the rollback netcode, but in an architecture with the SFU in the middle. And all of this is pretty easy very feasible to set up. We've already got support for different input types and the ability to switch between them. And we have room identification. We have a framework for room metadata. We can identify a host and live stream room from our netcode room. Once we add a little bit more to this, we just got to build up a little bit more on this. We've got an existing framework with a lot of different directions we can build out, right? And we can identify these different rooms, and so the live stream rooms can retain most of the logic they have now, and the rollback rooms can enforce these two different architectures. And then we can have a parallel play where you've got 2 or more screens going on all at once, where the host is playing, or sorry, not the host, but any client connected to it is playing on one screen, and then all the others are playing their own games. They're running their own emulators locally, and they can all see each other's streams in the screen, in the container of the emulator display. And this just adds kind of like a more fun social environment. Say you just want to chill out with your friends. You can very easily, we can have, as long as you unlock enough workers, and so you can divide these producers from the routers across workers, I think, even. So you can really take advantage of multi-core, and you can handle lots of different streams going different directions and stuff from these things. And you can, I don't know without really building it out and testing it more how much it can practically manage, but there, you know, it seems to be pretty effective from what I've seen so far. And you know, you can have lots of different streams on here and people playing different games, and even have like even have maybe you even want these games to have the ability to open up data channels. So this setup here by default is just data and video, or sorry, video and audio going back and forth between each client, right? So they all have one out and one in for video and audio to the SFU server. But they could send data as well if maybe like they want to have a Pokemon battle between two emulators in here. It's possible if the emulator's core supports link cable emulation, and the core plugs in to the emulator, and the emulator wraps the data from, so the core the core detects when in-game link cable activity is happening, and it tells the emulator that link cable activity is happening, and the emulator wraps it, and then the the emulator can then send that wrapped binary data as a data stream over the SFU to the clients, and you can have link cable emulation. And even let's say these guys are playing Xbox, Halo 1 or Halo 2 on Xbox, they can have LAN cable emulation, or they could do LAN cable emulation in these game modes as well. It really, that's up to them. Now, I know web emulator JS is never going to support Xbox, but here's the thing about all this stuff, is it's completely agnostic and unopinionated about what connects to it and the data that goes over it. And the only thing I'm making it care about is a token from Romm-M. And that's pretty much it. And so any emulator can send requests to the Romm-M API, and any emulator can get a token, and any emulator can gain access to the SFUs. So any emulator can join and become part of this ecosystem if they just make themselves compatible with the API endpoints and the calls that are used by the SFU for the data streams. However, it's not going to be easy because we have to rewrite netcode or add modules to the core netcode and implement them somehow at the code level on these emulators, the way similar to what was done with emulator JS to make it communicate with all this stuff. And it has to be, the emulator has to be responsible for handling a lot of the logic on its end as well. And so we can either collaborate or we can fork projects and import them into the ecosystem. And when it's all built out, we'll have a federated network of Romm sites talking to each other and SFU servers scattered around that open up channels with each other on demand and connect players in different rooms. They can all see each other's net play sessions, and they can all see what emulators each other are running. They can all see what ROMs they're playing. And they have a whole social experience with everything we've described. And it doesn't have to be locked down to just emulator.js. But once we've implemented all this other stuff, once we've got these different game modes, and then we implement this federated network, then the site becomes potentially quite popular. And then we can move on to soliciting other emulators to join the ecosystem. And then you can have Dolphin and other things connecting to the Romm ecosystem so that they can take advantage of sophisticated rollback netcode and scalable parallel play or live stream gameplay, scalable rollback net play or P2P net play, and they can do it all. They'll be able to do any. They'll be able to leave out any of this, too. They don't have to. Because on the emulator side, they will have to implement all of this. It'll be there working on this, and we'll have documentation sorted out once it's all polished and implemented well in the web emulator, in order to help them with their emulators. But they have to write the logic on their emulators for how to handle a lot of this stuff. And so, yeah. Anyways, I'm sure there's some other things I thought about, but I'm just going to show you some gameplay. Alright, I'm going to show some gameplay footage here on my phone. This is over the 5G. Now, it says that I'm a poor player here because if we look, this is not actually running on the phone, the emulator here. I'm streaming it. I've got 3 computers in front of me on the local network that are all receiving, that are all getting in the lobby. 1 laptop is the host, and there's 3 other devices connected for video and audio and input streams. So it's kind of pushing it here, and we're connected as the 4th player and playing over 5G on the phone. And
I'm just going to show that the performance is like over LTE and stuff. Video is pretty good, audio is clear, and the inputs are not really that delayed that much. You can feel it a little bit, but it's not much. Though you'll notice there are still some issues, like the audio does drop sometimes, and if you wait a few seconds, it will reconnect to the audio stream. And there's some issues if you're switching networks still that I have to sort out, and things to do with trying to switch to input mode while you're live. But you can have your input sent through the relay through the server, or you can have them sent P2P if ICE can be negotiated, or I'm stun. Yeah, so it's pretty playable interaction game over LTE, like not the worst, and so you can imagine it's pretty good for everything else that's less sensitive too. And this is like I said, this is streaming to four devices, so that's kind of like what the potential here is. Although I only have so many hands, so I can't show off all of them moving all at the same time. Alright.